Oh, it's recording now. Okay, John, you're the boss whenever you want to.
Okay, well, thank you very much for inviting me to speak in your seminar. I guess this is the first talk of your seminar, so I'll try to do a good job and set the standard high. And so this lecture is about two integrals, in fact, two matrix integrals that have kind of fancy names. The first one, which I'll denote IN, is called the Harish-Chandra-Itzhak-Zubair integral, which is often abbreviated HCIZ. And the second one, JN, there are various naming conventions and maybe some disputes about who this should be named after. Sometimes it's called the Bars-Green integral, and sometimes the Berzin-Gross-Witten integral. And in fact, Itzhak Bars, I believe, is your colleague at USC in the physics department. And okay, so these are two matrix integrals, which are going to be the subject of this lecture. And let me tell you what these are before telling you what they have to do with combinatorics. I mean, on the face of it, looks like nothing to do with algebraic combinatorics, but in fact, there's quite a lot going on here. And so here's a brief description of what the various objects that define these integrals are. So first thing to say is that what you're integrating over is the group of n by n unitary matrices, right? So complex matrices whose inverse is their conjugate transpose. And it's a compact group, compact Lie group, so it has a Haar measure, which is finite, and you can normalize it to 1, so it's a probability measure, and that's what the du is here. Okay, so it's integration over un against normalized Haar measure. And then the integrands are exponential functions on some data that can vary. So in particular, there's a complex parameter z in that exponential, and then there are two n by n complex matrices, A and B. And since these are nice holomorphic functions, if you integrate them over a compact set, you get back analytic entire functions. So these are perfectly well-defined objects, and they have a long history. IN was first studied by Harish-Chandra in 1957 in the context of some Lie theoretic things, which maybe I'll actually very briefly tell you about just as motivation. And JN was first studied by James in 1964. Somehow his name got left out of the Bkw integral in the context of multivariate statistics, which I can tell you about that, but it's not part of the talk. If you're curious, you can just ask me. And one thing to say right at the start is that there aren't any closed formulas for these integrals. You can't really evaluate them in any kind of explicit form, nothing particularly useful anyway. But one thing that you can say is that both of them are what are called hypergeometric functions of matrix argument. So they do have some special structure. In particular, IN is a hypergeometric function of two matrix variables, A and B, and JN is a hypergeometric function of the product of A and B. So I'll tell you a little more explicitly later on what that actually means. Okay, so here's the very brief origin of IN, and I thought that this could be interesting for people in this seminar because it's very much to do with algebraic combinatorics. And I assume that everybody sort of knows and loves Schur polynomials. So I figured I would include this as part of the motivation, even though strictly speaking, there are many other ways that this material could be motivated. So as you know, Schur in 1901, he classified the irreducible representations of GLNC, right? So n by n invertible matrices over the complex field. The rational irreducible representations are parameterized up to isomorphism. But one way you can say it is by configurations of n hard particles on the integer lattice Z, which I label from right to left, B1 down to Bn. And so here are two examples just to kind of set your dials. So if I put all the particles, these n particles, so I guess this is a representation of GL5 in my example. If I put all those particles on the first n non-negative integers, what that corresponds to in Schur's classification is the trivial representation, which just sends every invertible matrix just to the number 1. And if the rightmost particle jumps one site to the right, what you get is just the tautological representation, which sends every invertible matrix to itself. And so if you just, you can put these configurations of n particles you want anywhere on the lattice. Once you declare that some particular fully packed configuration corresponds to the trivial representation, and things which have particles to the right of that are polynomial representations, and things which might have some particles to the left are actually rational representations which are not polynomial, divided by some positive power of the determinant. Okay, so that's a very brief recap of classification of reps of GLNC. And not only did Schur classify them, he also gave a formula for their characters. So this is a very famous formula. If you want to compute the trace of some invertible matrix exponential of A acting in this representation corresponding to some particle configuration B, how do you do that? The character is given by a ratio of two determinants. Okay, so this is probably likely a familiar formula, maybe written slightly differently from what you're used to, which says that you just take this kind of, in the numerator, you have this n by n determinant of e to the ai bj, where exponential ai are the eigenvalues of your invertible matrix, and then the bj are the coordinates of that particle configuration, and you basically compare it to what you would get for the trivial representation, which is actually a van der Waals determinant. And this formula is the prototype for the Weil character formula in representation theory. So you have kind of an analog of this for lots of other Lie groups or algebraic groups, if you prefer. And but there's another way, and this is something that was observed by Harishchandra in 1957, which is there's another way to compute the character of an invertible matrix acting in a representation given corresponding to a given particle configuration. And it's this formula. Actually, this is the normalized trace, so the character divided by the dimension of the representation. And that corresponds to the fact that I'm taking normalized Haar measure here, which has volume 1 on the group. And here's the formula. So this is another expression of the Schur polynomials, if you like. It's kind of a more analytic expression of the Schur polynomials. And up to some kind of van der Waals looking thing in the eigenvalues of A and exponential of A. This is a matrix integral over UN. It's a nice, maximal compact subgroup in GLNC. And what you're basically doing here is this matrix integral e to the trace AU BU inverse is like the Laplace transform of uniform measure on the set of all Hermitian matrices whose eigenvalues are these particles B1 through Bn, right? So that's a kind of, it's a compact symplectic manifold. And this is sort of the beginning of a different way to do representation theory, which is often called the Kirillov orbit method. And in fact, this particular presentation of the characters of GLNC is the prototype of the Kirillov character formula, which expresses characters in terms of Fourier transforms or Laplace transforms of cojoint orbits. So that's where these objects come from. And there's sort of a similar story for JN, which I could tell you, but I think just one is good enough, and I'll tell you more about JN very soon. Okay, so hopefully that's starting with something that's quite familiar, and now some stuff that is probably less so. There's a totally separate motivation to think about these objects, these integrals, that comes from physics, specifically originally from an area of physics called lattice gauge theory, which is a certain model of strong particle interactions that was introduced by Kenneth Wilson in 1974. And actually, he got the Nobel Prize for that sometime later. And so what is lattice gauge theory? I'm not really going to tell you, but it's something that involves a choice of gauge group, and one of the traditional choices for that gauge group is UN, the unitary group. And in that context, it was pointed out by 't Hooft, who is another physicist who also won a Nobel Prize, that an interesting thing to do in this theory is look at the asymptotic behavior of lattice gauge theory when actually the rank of your gauge group goes to infinity. Okay, so when you're dealing with a UN gauge group, this is the large N limit of UN, and very much in that vein, these two matrix integrals IN and JN are actually kind of basic fundamental special functions in UN lattice gauge theory. So if you kind of believe this 't Hooft principle that you should look at the large N asymptotics of LGT, then looking at the large N asymptotics of IN and JN is a very kind of natural thing to do from that point of view. And in fact, physicists were the first people to do this, even though these objects were around earlier in mathematics. And in fact, there was a conjecture that they came up with right around 1980, just a whole bunch in a whole bunch of papers that were published almost simultaneously. And it's a little bit of a vague conjecture, as is often the case in theoretical physics. And what the physicists wanted to claim and felt was true, but actually there was a certain amount of trepidation. It's not that this was universally believed. There was kind of a lot of questioning of whether this is the case, is that IN and JN actually have kind of a very predictable large N asymptotic behavior, and they admit something that physicists call large N strong coupling expansions. And what that means is that IN and JN, as n goes to infinity, are asymptotically the exponentials of some particular asymptotic series. So some series G equals 0 to infinity, which starts at a power of n square and goes down in powers of 2 from that, so n to the 0, n to the minus 2, n to the minus 4, with some particular analytic functions upstairs in this exponential. Right, so these series are not claimed to be convergent, they're actually divergent, but that if you cut them off after any particular value of G, you're getting better and better approximations to these integrals, which you can't actually evaluate. And what they felt was true was that this should be the case if what they called the inverse coupling constant, which is this parameter Z, is small enough, right? So sort of like if Z was equal to 0, then both IN and JN would be 1, and this would be true. And what they also felt was that these terms and these asymptotic expansions, which I've denoted Fn superscript G and capital GN superscript G, maybe not the best notation, which they called large N free energies, are actually generating functions for something combinatorial. So this is where this has to do with combinatorics. And this part was really vague, but there's a kind of a principle in this part of physics, which is called gauge string duality, which says that FNG and GNG, these large N free energies, should be generating functions for some unspecified combinatorial invariance of genus G compact Riemann surfaces, connected compact Riemann surfaces, or smooth projective curves over C, if you prefer that language. And this is somewhat unusual in that they didn't actually have any guesses for what these invariants were supposed to be. It's often the case in physics that they sort of know the answer. They maybe don't justify it, but it turns out that they're right in the end. And this is not that situation. They actually didn't know what these things are supposed to be generating functions for in any more detail than what I've told you now. And this conjecture sort of entered mathematics in the early 2000s, along with kind of a big wave of interest in asymptotic random matrix theory and asymptotic representation theory. And it was nailed down very precisely by Benoit Collins and Elise Guillenet in 2004. And they really said this like in the language, formulated it in a way which you can understand as a mathematician and really think about very clearly. And so here's the precise formulation of this physicist conjecture. It really captures the essence of what their expectations were in lattice gauge theory. And it is that you can find some universal constant epsilon bigger than 0, such that for any non-negative integer k you choose, it could be 0, 1, 2, 3, anything you like, the logarithm of In, so what that really means is the principal branch of the complex log of this entire function In, is a sum of k terms, g equals 0 to k, n to the 2 minus 2g fn of g, plus a negligible error, right? So little o of the negligible in comparison to the last term in this finite sum, right? So this is really what it means to have an actual asymptotic expansion. And they conjecture that this error term is uniform for all complex numbers z, which are in a closed disk of radius epsilon, and all n by n complex matrices A and B whose eigenvalues are confined to a disk of radius 1, to a closed disk of radius 1. So in some sense, you know, this A and this B, they can be anything you want. It can be any n by n matrices, you know, n's going to infinity. And your only supposition really is that the eigenvalues of these matrices are filling up a disk of radius 1. Okay, and under these conditions, the coefficients of these asymptotic expansions should be analytic functions of the coupling constant z, and the eigenvalues of what's called the external fields A and B that look like this. Okay, so kind of a very special form. So you have like something that looks like a Taylor series in Z, and at each term of the Taylor series, well, let me talk about Fn of G first. You have what? You have a homogeneous bisymmetric polynomial of degree D. Okay, so what does that mean? These P alphas and P betas are the power sum symmetric polynomials, which I assume everybody's acquainted with, and won't go over that, but unless I should. Okay, just take it or leave it once. Okay, so this finite sum over pairs of Young diagrams alpha beta with D cells, the corresponding power sums and the eigenvalues of these matrices A and B normalized, right? So normalized power sums. This is n divided by the length of alpha and n divided by the length of beta, which has the effect that those ratios are actually, they have size at most 1. They're complex numbers of modulus at most 1. And moreover, the coefficients of these symmetric homogeneous polynomials at each degree D are actually integers, right? So FG alpha beta is some integer valued function on pairs of Young diagrams, and G capital G sub little g of beta is some integer valued function on just a single Young diagram beta, right? And the kind of name of the game here, really, there are two parts to this conjecture. Part one is to prove the analytic part of this conjecture, which is to show that this asymptotic expansion really does exist. And part two is to say, what does it mean? Okay, what are these integers, f sub g of alpha beta and g sub g of beta, and what do they have to do with compact connected Riemann surfaces of genus G? All right, so this is the, any questions on the formulation of this conjecture? It's like somewhat involved, but maybe not so terrible, right? So really the only things that are here are Taylor series and power sum symmetric polynomials. That's really it, okay? All right, so that's what the talk is about. It's about this conjecture of Collins and DNA from 2003, 2004. And the main result that I want to tell you about is that the conjecture is true, or after a long fight, it's actually can be proved. So this conjecture is true in the sense that these asymptotic expansions really do exist, and they really do have uniform error. All of this analytic stuff is actually true. And the meaning of these asymptotic expansions is that these coefficients, these free energies, Fng and Gng, are generating functions for some class of genus G Hermits numbers, which may or may not be familiar to you, kind of from very classical algebraic geometry, as counting branch covers of the Riemann sphere under some certain specifications, which I'll tell you about. So that's the result that I want to present to you. And I'll give you kind of a rough outline of the proof, but actually not that rough. I mean, there will be a fair amount of detail. And the first thing to be said is that the proof consists of 4 stages. So the first stage is exact formulas, by which I mean some kind of an understanding of these integrals In and Jn, which is actually valid for arbitrary finite n, and is sort of conducive to figuring out how these objects behave as n goes to infinity. And the second part is numerical asymptotics, where I'll compute the asymptotics of some sequence of numbers, which roughly speaking are like the Taylor coefficients of In and Jn. And the third part is what I'll call stable combinatorics, which is not analysis at all. This is really enumerative combinatorics, which is sort of in an ideal situation, what would the large n limit of In and Jn look like? And the fourth part is, once you understand this idealized sort of situation, which is purely formal, you have to convert it back into an actual analytic statement that is a correct solution of an asymptotic analysis conjecture. Okay, so that's the rough outline. All right, exact formulas. So I like exact formulas. I think I absorbed this kind of Borde and a Kunkov type of philosophy that the best way to solve an asymptotic problem is to have a nice formula that's valid for the limit, which you can understand well enough to take the limit, and that's really the only way that I approach asymptotic problems. And And getting such a formula is not so hard, actually. It's kind of a standard exercise in algebraic combinatorics. And so what you can do, this is a technique that's called character expansion in physics, but it's really just Fourier analysis on compact groups, in particular on UN. And in this particular setting, these sorts of expansions were actually first used by James in 1967 in this kind of multivariate stats context. Okay, so there's for each natural number n, there's a way to expand these integrals in and jn, and you can actually even forget about the fact that they were integrals at all and just think about them as these series. They're infinite series in Schur polynomials, okay, which we've already discussed. So what are the various things in play here? So these are infinite series in Schur polynomials, and so you've got a sum that's going over Young diagrams of all possible sizes, but at most n rows, right? And the corresponding Schur polynomials are the characters of GLNC, and this V lambda is the irreducible representation of the symmetric group SD corresponding to the Young diagram lambda. And this W lambda is the irreducible representation of GLNC corresponding to the Young diagram lambda. So in particular, it's important here that this inner sum is restricted to diagrams with the most n rows, which is telling you that this is actually a polynomial irreducible representation of GLNC. Okay. And so you can express these objects kind of as generating functions in terms of Schur polynomials, where the coefficients are somehow kind of comparing the dimensions of the representations of the symmetric group and the general linear group. So it has quite a bit to do with Schur-Weil duality, as you might expect. And the proof of this is fairly standard algebraic combinatorics, not so hard. And what this shows is that in and jn are hypergeometric functions of matrix argument, as I was saying earlier, in the sense of McDonald, which really means infinite series in either a single alphabet with Schur polynomial coefficients, or two alphabets. And more generally, you could deform the Schur polynomials and make them Jack polynomials. And that's a class of special functions which McDonald kind of cleaned up. It existed a little bit before and termed hypergeometric functions of matrix argument. Okay, so this is some kind of a initial foothold on these matrix integrals, which are very difficult to understand directly from first principles. Okay, and so we don't really want these character expansions. We're trying to make statements about the large n asymptotics of in and jn, which, if you call, involve not Schur polynomials, but Newton polynomials, right? Power sum symmetric polynomials. So what you want is to somehow convert these Schur function expansions to power sum expansions. And this also is not so difficult. Apparently nobody actually wrote it down before, but it's not so hard. This is something that okay, you can write it down in various forms. This is a good option. So this is expressing in and jn as infinite series, not in Schur polynomials, but in power sums, which are much more transparent. Okay, so this is what are the various objects here. The power sums, you know, z and n, you know, but there are other things. So in particular, the first thing is, what is this bold-faced p LISD is less than or equal to n? And what that is the probability that a uniformly random permutation from the symmetric group SD has no increasing subsequence of length n plus 1. Okay, so in other words, this is like this p LISD less than or equal to n is like the cumulative distribution function of this statistic, LISD. And so what these string expansions are saying is that, in some sense, the expansion of in and jn in power sums is like a generating function for the cumulative distribution of the longest increasing subsequence statistic. And then there's the stuff inside, right? There's this these angled brackets. What does that mean? What those are, those denote expectation against Plancherel measure on Young diagrams with a given number of boxes, but at most n rows. right? So what that means is summing a function f of lambda of a Young diagram against the weight that looks like dimension v lambda square, so number of standard Young tableau of shape lambda squared, divided by the size of Sn of d, the cardinality of the set of permutations in SD with no increasing subsequence of length n plus 1, right? So the fact that that is the normalization constant for this measure is just the Robinson-Shenstedt correspondence. Okay, and what are the things that you're taking the expectations of? What are the observables inside this angle brackets? Well, this little omega alpha is a central character of the symmetric group. So what that means is, if you take a conjugacy class C alpha in the center of the group algebra, right? So the formal sum of all permutations of cycle type alpha, Schur's lemma tells you that this acts as a scalar multiple of the identity in any irreducible representation, just has a single eigenvalue, and omega alpha lambda is that eigenvalue, right? And capital omega n of lambda is an explicit, maybe slightly strange looking positive function on Young diagrams with at most n rows. So what is capital omega n of lambda? Well, it's the product over the cells of lambda of a bunch of numbers, and those numbers are 1 plus the content of each cell divided by capital N. And this is a strictly positive function because it's being evaluated on Young diagrams which have at most n rows. So in particular, the most negative the content could be would be n minus 1, right? So this is always a product of positive numbers. So in particular, 1 over omega n was a well-defined thing. Okay, so that's what these string expansions are. And this is really the starting point of what I want to tell you about, which is once you have a hold of these string expansions, a perfectly reasonable thing to do is try to figure out what the n to infinity asymptotics of each particular coefficient in these series is. It's kind of like a little bit like the moment method in probability. You just try to compute the asymptotics of a bunch of numbers and then see if it actually can be transferred into knowledge of asymptotics of the function itself. Okay, so numerical asymptotics really means now that I have kind of these nice representation theoretic formulas, really for the coefficients of In and Jn expanded in nice power sum series, can I figure out the asymptotics of those coefficients? And the answer is yes. These string coefficients, as I'll call them, so I've denoted them here, In alpha beta and Jn beta, and I see the bottom of my screen is a little bit cut off. These formulas are good enough to figure out what the asymptotics of these things are. And there's a very nice answer here, a very combinatorial answer. And that answer is that the asymptotics of these numbers can be described in terms of the Cayley graph of the symmetric group, right? So the Cayley graph of the symmetric group as generated by the conjugacy class of transpositions, all transpositions. So this is the Cayley graph of S4 with a little bit of extra information. So I've labeled edges that correspond to multiplying by a transposition which swaps something with 2 by 2, and transpositions which are swapped with 3 are labeled by 3, and transpositions which are swapped with 4 are labeled by 4, color coded here. And this gives you a nice edge labeling of the Cayley graph. So in particular, in general, schematically, what does this graph look like? For arbitrary d, you have for each vertex in this graph, it's a regular graph of degree d choose 2, right? And so you have 1, 2 edge coming out, 2, 3 edges, 3, 4 edges, all the way around to d minus 1 d edges for a total of d choose 2, which basically means you take the transpositions in the symmetric group, and you put them in this matrix, and you keep track of what column they live in, right? So it's not so strange, maybe a little strange, but it's not so difficult to understand. And something that you can think about, a very classical enumeration problem in algebraic combinatorics, is counting walks in the Cayley graph of the symmetric group, in particular between 2 specified conjugacy classes. So you give me, 2 partitions, alpha and beta, and a number r, and you say how many r-step walks are there on the symmetric group that originate in the conjugacy class C alpha and terminate in the conjugacy class C beta and take a total of r steps. And the monotone version of this problem is looking for the subset of those walks which are actually compatible with this edge labeling in the sense that the labels of the edges you traverse form a weakly increasing sequence. So you can think about this kind of as the difference between like random walk and self-interacting random walk, right? So this is like the evolution of a particle on the Cayley graph of the symmetric group, which learns from experience. And once it crosses a road of value v, let's say, it refuses to use roads of lesser value than that. Okay, and that's what this combinatorics looks like. And okay, I don't know why my screen didn't move. That's not good. It's moving on my end, but not on your end. All right, I have to figure out what's happening here. I really don't know. Okay, I think I have to restart it. Sorry.
Jason, you can pause the recording for a moment.
Oh, I'll pause the recording.
Saying that we should restart the recording. Yes.
Oh, restart the recording. Yeah. So there's a theorem of myself and Ian Gould and Mathieu Gay-Paquet, which says that the string coefficients of the HCIZ integral IN and the BGW integral JN. So this was proved for IN in 2014 by Ian, Mathieu, and myself, and then for JN by me last year, are actually generating functions which count monotone walks on the symmetric group of given length and given boundary conditions. So in particular, for any number d, which is less than or equal to the rank of your group un, your string coefficients in alpha beta and jn beta expand as absolutely convergent series, which are computing these numbers, right? So they're generating functions which are counting number of R-stet monotone walks between specified conjugacy classes. And in the case of jn, they're walks which have to originate at the identity. And moreover, these are absolutely convergent series. Okay, so this actually gives you something of a window into what these objects might be asymptotically. As n goes to infinity, it seems like these objects should be generating functions which count monotone walks of arbitrary length and boundary conditions on the full tower of symmetric groups, right? So of any degree that you like. And there's some problems there. Okay, so this would be like taking a formal limit of these objects. And so what's going on is that these expansions of these string coefficients, which are absolutely convergent, these are like Feynman diagram expansions, if you like. So they're absolutely convergent. They give me a combinatorial interpretation of the coefficients of these analytic functions, but only the first n coefficients, right? So I can plug them in, and I get a description of the first n coefficients of in and jn, but I don't know the coefficients beyond that, right? And that's not so good, all right? So I mean, it's good and bad. It's good because we have something, and it's bad because if you only know finitely many terms in a series expansion of an analytic function, it could be anything. Anything could happen after that. So it's sort of seems like there's an analytic problem here, and in fact there is. And how can you deal with something like this? Well, this type of thing comes up. This is how topologists do it, and actually quite a similar situation. Suppose you have the unitary group UN, and you want to compute the homotopy groups of this manifold, right? So you want to compute pi1, pi2, pi3, and so on. You can do the first few homotopy groups of UN, and they exhibit this very periodic pattern. They alternate between the integers and the trivial group. And then if you go far enough, the homotopy sequence just becomes totally wild. You just can't predict what's happening. You get things like Z2 and Z12 and Z15, who knows? And in fact, like for example, this table shows that pi8 of U4 is like today currently unknown. However, the things in the stable range here are just totally perfectly periodic. And so what do you do in a situation like this? What Bott, who is a algebraic topologist, said to do is, the mistake you're making is you're trying to read this table along rows, and you should actually be reading the table along columns, because then you can figure all of this out. So in particular, if you take the limit along each column, which really means taking the limit of all unitary groups UN as n goes to infinity, which can be done in a meaningful way, right? Because they all embed inside each other, so you can take a direct limit. You get an enormous, not even locally compact group that's called the stable unitary group U, sometimes denoted U infinity. And you can say exactly what its homotopy sequence is. It's just periodic, okay, between Z and 0. And this is a part of a phenomenon that's called bot periodicity. And you can do exactly the same thing with these stable HCIZ and BGW integrals. You can sort of treat them as like enormously infinite dimensional objects in an n equals infinity limit, which would somehow correspond to trying to write down these integrals as integrals over the stable unitary group with your parameter n replaced by 1 over h, where h is an infinitely small number, and a and b are infinity by infinity matrices, and du is Haar measure, which doesn't exist on this not locally compact group. So obviously that doesn't really mean anything. It's quite problematic to define functional integrals like this. But our combinatorial picture that I just told you about from the numerical asymptotics part gives another definition, which is that you can do this formally, right? You can think about these stable HCIZ and BGW integrals actually as formal power series in infinitely many variables. So here they are written down. I have three formal alphabets, A, B, and C, with countably many indeterminates. The corresponding rings of symmetric functions generated by those alphabets. And then I and J are just formal power series in two formal variables, Z and H bar, whose coefficients are symmetric functions from those rings, okay? And as formal power series, these are perfectly well-defined objects. And they're kind of combinatorially quite explicit, right? So they're generating functions for all monotone walks on the symmetric group between arbitrary conjugacy classes in the case of I, and for conjugacy class identity to arbitrary conjugacy class in the case of J. And you can think about how these generating functions behave in the language of algebraic combinatorics. And in particular, one thing you can do is take a logarithm, right? So you can take logarithms of exponential generating functions. And what taking the logarithm does, as every good combinatorialist knows, is extract the connected component of whatever enumeration problem you're dealing with. So in particular, you can work out that log I and log J are these generating functions, which are counting monotone walks on the symmetric groups of all degrees, which are transitive, okay? So which have the additional property, in addition to everything I've told you, that their steps and endpoints together generate a transitive subgroup of the symmetric group. And that's what corresponds to connectedness in this problem. And that's the effect of taking the logarithm. Now, this is quite revealing, because if I actually drop this arrow over these HR alpha beta and HR beta, I get numbers that have been classically studied, right? Something that are called the classical double and single Hermits numbers, which count transitive walks between specified conjugacy classes without this monotonicity constraint. And those have been around for well over a century. And by a classical construction of Adolf Hermits, these walks actually correspond to counting maps between algebraic curves with certain specified conditions. So maybe I won't tell you full detail. Actually, this is fairly detailed. All right, but I may be running short of time. So if you can have, what my point is that there's a topological, in fact, even geometric interpretation of these numbers. So double Hermits numbers are counting branch covers from a surface of potentially higher genus to the Riemann sphere, which have certain ramification profile corresponding to these partitions alpha and beta. And in fact, such a branch cover exists if and only if alpha, beta, the walk length R, and the genus G of the surface satisfy a certain particular compatibility relation called the Riemann-Hermits formula. So you can write down these logarithms of the stable HCIZ and BGW integrals in terms of the genus instead of in terms of the walk length, and you get actually a formal version of the conjecture we're trying to prove. Okay, so in particular, log I and log J actually are formal power series which have a genus expansion interpretation. So G goes from 0 to infinity, and you're going down in powers of, you're going up in powers of 2, because H is like 1 over n, and H is this formal semi-classical parameter. And the coefficients of these series are genus-specific generating functions for these monotone, double, and single Hermits numbers, right? So the first term is genus 0, the second is genus 1, and so on and so forth, okay? And so this gives you a pretty good idea of what's going on here. And the question is, can you take this stable combinatorics and convert it back into actual hard analysis? And the answer is yes. It's pretty hard, but you can do it. And especially if you have like 4 months where you can't leave your house, is a good time to try and work this stuff out. And so I'll tell you some recent 2020 theorems that actually say how you can rigorously transform this sort of formal solution of the problem into actually an analytical solution of the problem. And it's quite remarkable the way this actually all works out. Okay, so basically the point here is that I know what the answer is supposed to be, and can I prove that that actually is the answer, right? So I have these formal expansions. Are they actually right if I descend from n equals infinity to n going to infinity? And you know, can you do this just by setting this formal semi-classical parameter h bar equals 1 over n in these formal statements? Yes and no. So the answer is kind of. So part of this works really well. So let me use this notation. I'll denote by d rho n. This is going to be a polydisk, either of dimension 2n plus 1 or n plus 1 in complex space. And I'll just use this symbol ambiguously to mean either. And because I need, you know, C2n plus 1 for in, and I need Cn plus 1 for jn, but actually the computations are the same. And I'll denote by just a double bar row the sup norm on each of these closed polydisks, even though this is actually a sequence of norms depending on n, and the dimension of your space is growing. It's helpful to think about this as a kind of a norm on just one polydisk. And we have explicit candidates for the large n free energies, which are in this Collins-Guillenet conjecture now. If this conjecture is true, they have to be just these generating functions for monotone double Hermits numbers of specific genus. And the question is, are those actually analytic functions, right? So if I replace h with 1 over n, are these series actually summable? And the answer is as good as it could be. They're okay. Once again, the screen froze. That's extremely frustrating because things are just starting to get interesting. So I have to go through this one more time. I'm very sorry. I don't know why it keeps disconnecting. Okay, we're back. All right. Everybody can see it again? Okay. So in fact, this just works great. All right. So you can, there exists a universal constant delta such that for whatever your n is and whatever your g is, these series are actually uniformly summable on this polydisk d delta n. And moreover, because of the form that they have, you know, your p alphas are divided by n to the length of alpha. This defines for you two sequences of analytic functions of 2n plus 1 and n plus 1 complex variables whose sup norm is actually uniformly bounded in n. So this is like an analyst's dream. I mean, you can just, it seems like you're just right about to prove this conjecture because you can just take these sums of analytic functions and just compare them directly to log in and log jn, right? Everything is very specific, is very explicit here. So you could just think that maybe all this means is I just have to compare analytic functions on a certain small polydisk in C2n plus 1 or Cn plus 1. And now there's a bit of a problem. It's actually a big problem, which is, okay, great. We know what the target analytic functions are supposed to be, but there's a problem with log in and log jn, which is, do you even know that these things are defined in analytic for all n? And what I mean by that is if you want to take the log of an analytic function, you had better be sure that you're taking the log on a domain where this function is not equal to 0. And this is exactly a problem because these integrals in and jn involve complex parameters, right? They're oscillatory integrals. This is why people in probability, when they study exactly these integrals, in fact, they restrict to real parameters so that the integrals are actually integration of a positive function against a positive measure. And what you're doing is essentially trying to develop some kind of a large n version of Laplace's method. But this is not that, right? If you allow complex parameters, your integrals could actually vanish, right? Your integrals could actually vanish. These are entire functions. You know that their value at 0 is 1, but it might be the case that no matter what epsilon you pick, the analytic varieties, which consist of the vanishing set of in and the vanishing set of jn, are going to intersect that disk for infinitely many values of n. And this would be like fatal to this conjecture, the complex variables version of this conjecture. And the picture in the z-plane is that, okay, yes, you have these entire functions and they have some zeros somewhere out in the z-plane, and you don't have a 0 at the origin. So for each fixed n, you can define your function and take its logarithm in a neighborhood of the origin, but that neighborhood might actually collapse when n goes to infinity, okay, because these zeros move as functions of n. And so you have to rule that out. And this is there's a great trick for doing this. I'm very proud of this trick. And it's once again to go back to the stable combinatorics to somehow see that this can't happen. And the way to do this, or a way to do this, is to look at what the stable HCIZ and Bkw genus expansions look like before taking the logarithm, right? They look like I is equal to exponential of this formal infinite sum of h bar 2g minus 2 fg. And since these are all formal series, you can partition that into, you can factor it into two terms for any k you want, and divide through by the part that's exponential of a finite sum. And what's left is the exponential of the generating function for covers whose genus is at least k plus 1. Okay, is at least k plus 1. And what does that mean? It means that your these quotients, right? So I divided by the exponential generating function for connected branch covers of genus anywhere between 0 and k. Well, that's gonna make possibly disconnected branch covers, each of whose components has genus k plus 1. And the only surface of negative Euler characteristic is the sphere, which is guaranteed not to occur as one of these components. So you get these beautiful topological factorizations of these quotients, not just I and j themselves. Sorry, that second I is supposed to be a j, where you have these genus expansions which are starting at g equals k plus 1 instead of at g equals 0. And I've been told by some people in physics that this is somehow reminds them of something called the Bkw expansion, but I don't really know what that is. Okay, and so what does this mean? This is like a formal concentration inequality, right? So this is basically saying if you look at these sums and you subtract off the constant term 1, you're actually getting power series that lie in the principal ideal generated by h bar to the 2k, right? These series are multiples of h bar to the 2k. And so this is saying that formally, these generating functions are big O of h to the 2k. And this strongly suggests that even though these are, like in the analytic world, these are oscillatory integrals, they actually do exhibit some kind of a localization feature. They actually do concentrate. And the analytic version of this, which is not easy, is the following: that there exists some gamma, which is at most delta. So delta is the domain on which your candidate functions f and g are defined, such that the supernorm of 1 minus in, so in's a nice entire function, divided by this non-vanishing function, actually is big O of n to the 2 minus 2k uniformly on that domain. And this localization theorem, that gets rid of our potential vanishing problem, right? Because this says, for example, if I take this out to k equals 2, I'm getting the discrepancy between 1 and in divided by exponential sum up to genus 2 is decaying like order n to the minus 2. So in particular, as n goes to infinity, this quotient of in with a non-vanishing function is actually lying in a small disk around 1, can't be 0, okay? And so this localization theorem for the oscillatory integrals in and jn basically clinches the argument. So this is the non-vanishing corollary that I just told you. And just how does this work? It's really pretty subtle, actually. So the proof of this localization feature for these oscillatory integrals really says, you have to go a little bit farther out in the string expansions of in and jn. So we know their first n terms, but actually what you need is their first order n square terms. And why is that? That's because you can approximate in and jn by an exponentially small error if you look at their expansions out to degree n square. This is basically because the dimension of un as a real Lie group is n square. And the problem there is that we don't actually know that these sort of Feynman type expansions of our string coefficients are actually valid. We only know that they're valid up to order n. We somehow have to extend this to order n square, where in fact these expansions are a priori divergent. And it's something of a miracle that even though they're divergent, up to order 1/4 n square, as long as you're below that cutoff, these divergent series are actually remain valid as asymptotic expansions. If you stop them after finitely many terms, the error incurred is negligible in comparison to where you stopped. And the reason for this is really like rooted in the asymptotic representation theory of the symmetric group. It has to do with the shape of a large Plancherel random Young diagram, or if you like, the fact that the expected length of a longest increasing subsequence of a random permutation from SD is like 2 square root d, and that 2 square root d is exactly this 1/4 n square. And you can use large deviation properties of this kind of limit shape theorem for longest increasing subsequences to actually show that this divergent Feynman expansion remains valid actually exactly out to that order. And so this is, and what this says is that if you approximate in and jn by their string polynomials out to degree n square, they behave up to an exponentially small error, so in particular smaller than any polynomial, exactly like the formal or stable HCIZ and BGW integrals. And what that means is that you can now kind of really do analysis with these objects in exactly the way that you would hope from the point of view of like several complex variables. Okay, I'm not a several complex variables person, but I go where the wave takes me. You just got to do it. And this is enough to clinch the analytic argument. Okay, this is enough to clinch the analytic argument. So this conjecture amounts to sort of checking that each of these, now you can legitimately compare log in scaled up by any power you want to however many terms in the sum you want. And you just have to show that the error uniformly goes to 0, okay, in some epsilon neighborhood of the origin in C2n plus 1 or Cn plus 1. And that can actually be done using these localization inequalities. You might notice that this quotient in as over exponential sum from g equals 0 to k, n to the 2 minus 2g of your g candidate can actually be written in terms of these error functionals delta n k, and really this is enough to show that these error functionals are actually uniformly bounded in n, which with a little bit of analysis is actually enough to show that they converge uniformly to 0. The reason for that being that if you have a sequence of analytic functions and you know that its Taylor coefficients converge to 0, then if that sequence is uniformly bounded, that's enough to say that the functions themselves uniformly tend to 0. Okay, that's a little bit of standard complex analysis, slightly more complicated for several complex variables, but this can be done. And you get the solution of this problem, of this conjecture that was sort of posed vaguely by these physicists in 1980 and reformulated by Collins and Guillenet in a very precise way in 2003, 2004. And it's all true. In fact, so you have complete asymptotic expansions, so valid to any refinement of approximation you want. of log in of log jn, which are valid in a uniform but sort of like absolute neighborhood of the origin in high dimensional complex space. And the terms of those asymptotic expansions really are generating functions for these monotone double Hermits numbers and monotone single Hermits numbers of genus G. And I notice here I actually wrote this FNG and GNG in the wrong order. Okay, I should really pick better notation. So these, you should transpose these two things. Probably at this point you're so confused that it doesn't matter. But okay, and that's sort of the path to the solution of this conjecture. And like there are just an enormous number of things you can do with this. For example, you can write down the asymptotics of Schur polynomials using this theorem in a very complicated double scaling limit, where both the diagram indexing your Schur polynomial and the number of variables grows to infinity. And people in asymptotic representation theory, they know how to do this when the diagram grows, but not when the number of arguments of the Schur polynomial is growing. And this really kind of breaks through that barrier. And in terms of physical applications, this is actually like a meaningful kind of formulation of something that's like large N gauge string duality. And you can actually use this to sort of at an analytically rigorous level prove some kind of open questions from quantum Yang-Mills theory and stuff like that. So it's very happy with the result and the way it worked out, and I anticipate that it can be used for quite a number of things, maybe even in algebraic combinatorics that any of you might be interested in, as it has to do with the asymptotics of Schur polynomials or other special functions of that type. Okay, so maybe I'm slightly over, but I had a couple of blips in my screen sharing, so I hope you're not too annoyed. And thank you very much for your attention.
Great, thanks.
Yeah,
so thank John. Yeah.
A beautiful talk.
Yeah, very nice.
I guess, do we clap on
I don't
Zoom?
know. Yeah.
It seems a little silly.
It's a little silly.
Okay. I'll just imagine that you're clapping. It's okay.
Yeah.
Yeah.
Any questions? So I had a question.
Sure.
So these monotone paths come up. So do you know if anyone's looked at kind of a more refined enumeration where you look at all paths, but you kind of look at a generating function where you count like number of descents?
Yeah. So what people have looked at, this theory of these monotone Hermits numbers kind of like sparked off some sort of surge of interest in combinatorial deformation of Hermits numbers. And it's not quite what you're suggesting, but what people are looking at is basically ways to put arbitrary parameters on the edges of this Cayley graph so they can be specialized in any way you want. And that theory has been quite well developed now. And in regards to your question, it's sort of not inconceivable that you could maybe tune these multi-parameter Hermits numbers to try and pick up other statistics like descents and that type of thing. I don't know that is true, but it's not impossible. Yeah.
Okay. And so I guess you could also maybe tune the parameters, or set some parameters to 0 so that you'd be doing a Cayley graph with like a smaller generating set.
Yes, that's right. You could do that. You can set various parameters to 0 and like calculate things like star transpositions, which are like only swaps with the largest letter, things like that.
Mm-hmm.
Yeah.
Okay.
Yeah.
Well, why do people study both of these integrals together? I mean, did they get discovered at the same time, or?
Yeah, they got discovered almost simultaneously, and they both are. So they're both needed to figure out what's happening in this subject of lattice gauge theory, and roughly speaking, this is really roughly speaking, what's going on is that like in this theory, you have a random unitary matrix on each edge of a lattice of given degree, and you somehow want to take an expectation of some random variable, which is called a Wilson loop variable, as it goes around some kind of homologous chain in this lattice. And in order to do that, you can sort of package these expectations in terms of these matrix integrals In and Jn, and like reduce the problem to finding what their asymptotics are to do the large N limit of UN lattice gauge theory. So that's where they come from in that context.
Okay, thanks. Any other questions for Jonathan? Okay, well, thanks so
All
much
right.
for a beautiful talk.
My pleasure. Thank you.
Yeah, thanks. Very nice. Very nice.
Okay. So goodbye. Well, thank you very much. Yeah.
Yeah.
And
no other questions.
hope to see you all in,
thanks for talking.
real
Thanks
life
for starting
at
off
some point.
Semester. Yeah. Good
Yeah.
talk to start the semester with.
Okay, great. All right.
Okay, bye.
Take care. Bye.
Let's see, so I guess we should stop the recording or?